Hi, I'm Marthaler, and I'm here to talk about quantum computing and the future of sustainable materials. But before I do this, let me shortly introduce my company. I'm a CEO of HQS Quantum Simulations, and me and my co-founders worked together at the Karlsruhe Institute of Technology. And then in 2017, we founded the company to work on using quantum computers to simulate materials and chemical processes. And accordingly, when we started directly, we started immediately to work with companies in the material science and chemistry space like Bosch and BASF. And since then, we have grown to about 40 employees and are at the forefront of trying to use quantum computers as an innovative product to kind of design new materials. And let me also quickly thank all the funding agencies, since we also work on a lot of research grants. So there's the Ministry of Research and Science and the Ministry of the Economy and Climate in Germany. And of course, there is EU funding, for which we are immensely grateful for supporting our work. As we look to the future, there are really many important topics where it's clear that we need and we want kind of better materials for various areas. There is, of course, the whole topic of the improvements in our existing electronic devices, where it's very clear that a large amount of material science research is happening. But what I really want to talk about, of course, today is the topic of sustainability and the critical need for better materials for the future of a sustainable economy. I have here several topics listed, and of course, very obvious is the need for good or even better battery materials. Then a very important topic is biodegradable polymers, but less flashy, but also really quite important, is the need for improved and energy efficient catalysis. And let me take these three topics and go through them a little bit more in detail. For obvious reasons, battery materials are of course very important. It is very clear we want to switch in the future to electric cars. Therefore, every car will need a battery, and ideally this battery should also be able to store a lot of energy and store it over a long time and have a huge amount of cycles for which it will be stable. Similarly, we will need long-term storage for the electricity from renewables as we switch, energy production, electricity production more and more to renewable sources like solar and wind. Now, current battery materials are similar to lithium cobalt oxide, which can already be, these type of materials can already be quite good, but come still with quite a few challenges. For example, cobalt is needed in general, and mining cobalt can create substantial environmental challenges. But not only this, the long-time stability of batteries currently is also limited, since on these lithium metal anodes we have growth of dendrites. This means we have basically a growth of additional material on top, and this can lead to kind of damages in the long run of these batteries. Therefore, it would be really important to look at, for example, metal surfaces and understand effects on metal surfaces. And here simulation can be, for example, quite sensible. I'm just showing here a very generic problem with a copper surface, because these type of problems can be important everywhere, and simulating them and understanding them better and therefore developing better materials could be very important for batteries and for many other topics. Now, if we look at polymers, it's very clear that this is also an extremely important topic. It's very famous to look at these kind of all the plastics that you see in the seas. So plastics are used everywhere, and we can see the plastic trash accumulate in a way in our seas that is not sustainable in the long run. Now, of course, if you think about what we do in the future, it would be very nice to have biodegradable plastics, which would then consist of biodegradable polymers. But this is fundamentally, of course, extremely difficult, since, of course, the reason why we use plastics is because they are so stable. So designing polymers that degrade exactly under the conditions that you want and not under the conditions that you don't want is still very challenging and an unsolved problem, but clearly hugely important going forward. And then, of course, one also has to think about how to mass produce these type of polymers in the future in a way that kind of matches the cost of current plastics. Each of these kind of polymers is very long, and then the plastics themselves are formed by many of these long chains of polymers. But even investigating smaller parts of each polymer can help you to understand the conditions under which it can degrade. And this is something where also simulation can help a lot and can be very important to design new materials in this space. Which brings us to the last topic, energy efficient catalysts. Catalysis is super important in basically every chemical process, so everywhere where any type of material is produced in the chemical industries, catalysis is used to reduce the energy consumption that is needed. Because a chemical process happens normally at a certain temperature, and this temperature can be lowered by the use of catalysts. And therefore, improving various catalysis processes can be hugely beneficial and reduce the energy costs in the chemical industry. And as one very kind of significant example, nitrogen fertilizers are extremely important for our whole kind of food industry, but alone the production of nitrogen fertilizers consumes 2% of the overall global energy production. So even kind of small gains in kind of the production chain and the production efficiency of nitrogen fertilizers could have a huge impact on saving energy globally. And also here, simulation could be very important because the processes that happen in catalysis often involve relatively small molecules and relatively few molecules. Shown is here an example where I have this blue atom, which is ruthenium, atom often used for catalysis. And the process shown here is kind of the chemical reaction from CO2 to CO2H2, an acid. And this is a process which has been proposed for carbon capture, which can only happen at kind of sufficiently low energies if very good ideas have been created for the catalysis processes. So in many ways, this topic is hugely important and one where simulation could be very helpful kind of to gain new ideas and new insights. And now, as I explained all these topics, let's now get to the point, because we want to connect this to quantum mechanics and accordingly to the quantum computer and discuss a little bit how the quantum computer can help in solving these problems and designing new materials. So fundamentally, what do we believe the quantum computer will do? Fundamentally, you might have heard that the quantum computer will solve various problems faster than conventional computers. And that is true, but in general, it's not simply faster, but it is that the scaling of these problems is better on a quantum computer than it is on a conventional computer. And let me now introduce this concept of scaling a little bit more. Scaling means you have a certain problem, you solve it on a conventional computer, and with this type of problem, a certain size is associated. And this means, now you solve it at a certain size, and now maybe in the future you want to solve a bigger problem at twice the size. And so, of course, your computer will take longer. But how much longer? This is a major point. Sometimes, many problems that you have might scale very nicely, meaning as you double the size of the problem, the time you need to solution might also only double. It's very good for you. And this is indicated here in this figure by this magenta line, where you have a very smooth kind of increase of the time to solution with the size of the problem. However, other problems, and very important problems, are known, which are indicated by this green and the orange line. And here it is so that if you kind of increase the size of the problem you want to solve by a little bit, the time to solution can really start to explode. And this magenta line, so the really nice scaling, is known as linear or polynomial scaling, and the magenta and green line are known as exponential scaling. And what can the quantum computer do? So for some problems, it can take a problem that scales on the conventional computer, like the orange line, and bring it down to a problem that scales on the conventional computer, like the green line. And that is called polynomial speedup. However, more excitingly, it can actually also take sometimes problems that scale like the orange or green line, like exponential on a conventional computer, and bring it down to a scaling like the magenta line. And that is called exponential speedup, and that is what we seek. Because there, fundamentally, we can start to solve problems at a certain size that will remain probably basically impossible on conventional computers. Now, how is that possible? Let's dive a little bit into the basic components of the quantum computer, and let's do this by comparing it to the basic component of our conventional computer. And to do this, let's compare the bit, the basic component of your conventional computers and all our conventional digital electronics, compare it to the quantum mechanical bit, the qubit, the basic unit of the quantum computer. The bit, as you might know, can take two states. The states are depicted here as an arrow. And let's look at this. So basically, it can point down, and this is the state 0 of the bit, and the arrow can point up, and this is the state 1 of the bit. Now, the state 0 and 1 in a qubit can now be, the qubit can now be in both states at once. So in the states 0 and 1. And this might sound very kind of strange and so on, and to a large extent it is, but as long as you only look at a single qubit, you can actually depict this in a very simple way by depicting the state of the qubit again as an arrow, but now instead it only pointing up and down. This arrow can point in every possible direction. And actually on this level, this turns out to be bad. Why is this so? Think about the stability of the bit and the qubit against external perturbations. If you have external perturbations and your bit is supposed to be in the state 1, meaning the arrow is supposed to point up, then something kind of changes this direction. But this arrow still roughly points upwards, so it's still in the state 1, everything is good. For the qubit, this is obviously different. Now you want to have a situation where you can have a state pointing in every possible direction. Therefore, any perturbation now actually creates an error in your computation. Now, but what is good about the qubit? This is best explained if we look not at one bit and one qubit, but at many bits and many qubits. And I have depicted here 4 qubits versus 4 bits. 4 bits can, store one 4-bit number. So far so good. Now, 4 qubits can now again be in all possible states at once. And this means it can be in all 16 possible states of these 4 bits at the same time. And now think about how this scales. 4 qubits can be in 16 states at once, 5 qubits in 32, 6 qubits in 64, 7 qubits in 128. So you see here, you have an exponential scaling of the number of states you can be in at the same time. And this is, of course, the reason why some of these exponential scaling problems on conventional computers can suddenly be solved in linear time or in polynomial time on a quantum computer. Now, fundamentally, we also know how we solve this problem with the errors. In principle, it's possible that we take many of these qubits and create one effective logical qubits using these many qubits. So you create some type of redundancy if you want. And then you can create logical qubits that are basically completely error-free. However, the number of physical qubits that you need to build on a chip to create one logical qubit can be very high. I would say it depends a little bit on the details, how it's done, but let's say it's somewhere between 500 and 50,000 physical qubits you need to make one error-free logical qubit. And now let's look a little bit forward about what this means for using quantum computers. If we want to say we want to have 100 logical qubits, which is a number picked because, at this point, clearly the number of states we have in superposition, 2 to the 100, is so large that, this could never be done. Nothing similar could be done on a conventional computer. So if you want to have 100 logical qubits, we would need somewhere between 50,000 and 5 million qubits integrated on one processor, physical qubits integrated on one processor. And we can say, okay, let's assume we started with like 5 or 10 qubits in 2018, and we now double the number of qubits every year, similar to how the number of transistors doubled on our conventional computing chips. Then we would achieve fully error-corrected quantum computing at earliest in 2031 or a bit later in 2037, depending on our assumptions about quantum error corrections. So there's still some time to pass, and of course, will this scaling really happen remains to be seen. Currently it's looking good, but let's see. This might still be shifted out a little bit further. So of course, we want to think about, can we use quantum computers even without full quantum error correction? And therefore, we want to use the most optimal application for quantum computers. And this, of course, is quantum simulation. Let's talk a little bit about quantum simulation, because this now connects the quantum computer to this topic in chemistry that we discussed at the beginning of the presentation. Now, quantum simulation basically means that I solve problems that are intrinsically quantum mechanical. And these problems I always have when I want to, calculate properties of a material, calculate properties of a molecule, calculate properties of a reaction of two molecules, and so on. And this is, of course, because fundamentally, everything is described by quantum mechanics, but as size scales become larger, if we want to simulate a whole car or a plane, then, of course, the laws of quantum mechanics are sufficient, and only at these small scales of a molecule or of a material, we need to really consider the laws of quantum mechanics. I show here a small molecule, which is already quite interesting. It's a parabenzene. And if we want to simulate this molecule, what we do is first we fix the position of all the atoms, and then we look at all the electrons of these atoms. And these electrons kind of zip around these atoms and form what we call orbitals. And actually what I show here are two of these orbitals. These are the localized orbitals of kind of two electrons that correspond to the colored atoms on my last slide. And now it's not quite the case, that these electrons just zip around the atoms. It's quantum mechanics, so it's like a probability distribution. But in some sense, you can imagine these clouds as kind of the points where the electrons is more or less likely to be. So this is a molecule, and now what we need to do is we can find these molecules with like rough approximations. It's again, we know this is a molecule, but now if you want to solve more precisely on a quantum computer, kind of calculate more precisely what the properties of these molecules are, we need to keep track of the state of these orbitals. And there can be an electron in this orbital, or there can be no electron in this orbital. And this means, you have a state where this is occupied, a state 1 orbital, and a state 0 where the orbital is unoccupied. And this, looks exactly like the state of a bit or, a quantum mechanical bit, since it's quantum mechanics. And this orbital can be in a superposition of there's an electron in or there's no electron in. And now how does this look if, we want to not keep track of a single orbital, but we want to keep track of 4 orbitals? Then we now need to keep track of all 16 possible states of these orbitals, meaning we need to keep track of 16 states at once. And how does this scale? If I now want to keep track of 5 orbitals, then I need to keep track of 32 states, 6 orbitals, 64 states, 7 orbitals, 128 states, and so on. And as you see, this is exactly the scaling that you also have if you look at the states you have in your qubits. So this problem maps 1-to-1 to qubits. And then for obvious reasons, this is also a problem which would scale very badly on a conventional computer. So, as you add the number of orbitals you want to keep track of, which would be the size of the problem, your problem starts to escalate in difficulty in an exponential way. However, since it maps so naturally to the number of qubits, so each orbital maps to 1 qubit, you actually can, in a very clear fashion, motivate why you get this exponential speed up. And therefore, quantum simulation is one of the most optimal topics for quantum computers, and therefore it's very interesting for many people to work with, or to work on at this point. Now, a question still remains: is it sufficiently optimal problem such that it can even work without quantum error correction? It's of course not clear, but many people work on it, and it's generally considered the most probable case where people really believe that it can work even on near-term quantum computers, maybe with a certain amount of error correction, but not with a completely error-corrected large-scale quantum computer. But let's now look a little bit even deeper into things in the kind of material science development cycle and how quantum simulation can add in this cycle. If we look at the development cycle in the chemical industry, then it has the following form. First, people think about design, meaning they fundamentally think about kind of what type of materials could help for a specific purpose. And then they try to synthesize it, which is a lot of work. So then you synthesize and then you do analysis. So this analysis, of course, is you test if the material has the properties that you want, but then you also fundamentally have to even check if you have synthesized the right type of material that you kind of wanted to have and that you believe has specific properties. And in this cycle, the type of simulation and the type of quantum simulation that I described can come in and help you a lot during the design stage. So where you really think about what kind of materials should I synthesize. You first would test a lot of materials on a computer and see do they have the right properties, and then go to the synthesis stage. However, quantum simulation and the quantum computer then can also help a lot in the analysis stage. And this I want to show you a little bit. So a topic where the quantum computer can help a lot is nuclear magnetic resonance. So where does that play a role? What you do, generally, you synthesize your molecule and then you want to know, do I have really the right type of molecule? And for this, you do various measurements. And the typical measurements people do is nuclear magnetic resonance. And this basically means you have your molecule in some kind of liquid, you put it in a very strong magnetic field, and then you shine microwaves on it and kind of receive some microwaves back. And these microwaves come with a certain frequency range, which is seen here. So these kind of peaks you see in this orange plot correspond to microwave intensities at a certain frequency. And then you try to look at this and try to see, okay, is this really corresponding to the molecule that I want to have? And this, of course, sometimes very difficult to know. I mean, the connection between molecule and this spectrum can be established. That's why these measurement techniques are, of course, used. But sometimes it could be really helpful if you can do a calculation of the spectrum before you measure it. And this can actually really be very nicely put on the quantum computer. So there's an extremely nice connection between calculating the spectrum and calculating something on the quantum computer, where you first, you extract some simple properties from these molecules and then calculate the time evolution of a spin problem, which also directly one-to-one maps to the qubits on a quantum computer. And since it directly basically means you just use the qubits in and by themselves, because there is a direct correspondence between the problem you want to solve in nature and the physics of these qubits, it is of course a problem that is difficult to solve on conventional computers and really ideally to solve on quantum computers. And after some measurements, you can extract the spectrum. And I wanted to shortly approach this problem at the end of my talk without explaining it too much, to just show you some actual results from a quantum computer, because this is the actual major problems we are currently working on. So what you see here is a spectrum calculated for a small molecule with 2 spins, where we compare a direct kind of theoretical solver on a conventional computer. I mean, the problem still has a size such that you can solve it on a conventional computer, with a solution from a quantum computer, in this case the IBM Q. And as you can see, it fits quite well. Unfortunately, current quantum computers are still quite a bit noisy. So this noise and perturbation problem that I described at the beginning still remains a little bit larger than optimal. And here we look at a little bit larger problem. And you see there's still a quite clear correspondence between the signal from the IBM Q device and our direct solver. But the noise is also quite visible. So improvement in the current hardware still need to be made. But actually, even without full quantum error correction, it should be possible to improve the current qubits quite a bit further than what is shown here. And so it remains quite possible to, for example, use this type of techniques during many stages of the material development cycle of the chemical industries, be it in design or be it as shown here in the analysis part. And with that, let me conclude. As we look towards the future, it is quite important to develop new materials. This will really be one of the most important issues as we want to move towards a sustainable economy. And since developing materials is intrinsically connected to quantum mechanics, we think that the quantum computer can really help a lot in accelerating these topics. Thank you.